This video is going to look at section 2.5, complex numbers. Review some of the things you remember from Algebra 2 about how to perform operations on complex numbers and also find complex zeros of quadratic functions. So really quickly, a review of complex numbers. Remember that there is complex numbers written in the form a plus bi, where a is your real part and b is your imaginary part. So when you do some operations with complex numbers, all you're doing is kind of working with like terms. So if you think about it as the real part as your like terms and the non-real parts as like terms, you can combine them very simply when you're doing addition and subtraction. So for example, when I have 7 minus 3i plus negative 2 plus 4i, when I want to combine these, I'm going to combine the two real parts. So 7 and negative 2 is going to give me 5. And then negative 3i and positive 4i, when I add them together, is going to give me positive 1i, or just I. So this answer is just going to be 5 plus I. We can do the same thing with subtraction, just don't forget to distribute your negative. So obviously if you're going to distribute your negative, this is going to go to both of these terms. So it's like saying 7 minus 3i minus negative, which becomes plus 2, minus 4i. Combining our like terms, we've got 7 and 2, which gives us 9. And negative 3i and negative 4i, which gives us negative 7i. So 9 minus 7i. So when you're adding and subtracting complex numbers, you're just basically combining them sort of like terms. The real parts get combined together and the non-real parts get combined together. When we multiply, we need to remember that obviously we're going to multiply like regular, but there's something special that we remember about complex numbers. We know that I is really the square root of negative 1. So I squared is going to be negative 1. Anytime I have a problem where I have anything other than I, like I squared, I cubed, something to the higher power, we want to make sure we simplify it as far as possible. Here's what we're going to do for this problem. So I'm going to go ahead and multiply. Obviously we got 7 times negative 2 is going to give me negative 14. And then 7 times 4i is going to give me 28i. And then I've got negative 3i and negative 2, that's going to give me positive 6i. And then negative 3i times 4i is going to give me negative 12i squared. When I multiply, I go ahead and line up like terms, just makes it easier to combine the two. So I can see I've got negative 14, we've got plus 34i. And then when we go to write this, we know it's going to be minus 12 I squared, but I squared becomes negative 1. So this is really like saying plus 12. So now all I need to do is combine my two real terms, which I've got negative 14 and positive 12, which gives me negative 2. So negative 2 plus 34i is my final solution here. Now, how you deal with division is a little bit different. In order to get rid of a complex number in the denominator, we multiply by something called the conjugate. So let's review real quick what the conjugate is. When we look at complex numbers for the conjugate, for example, a plus bi, the conjugate is going to be a minus bi. So the only thing that changes is the sign between the real and the non-real term. So if I had, for example, negative 3 plus 5i, the conjugate would be negative 3 minus 5i. So the first term never changes. The only thing that changes is the sign between them. If I said it was 4 minus 3i, then the conjugate would be 4 plus 3i. You notice something special about the complex number and its conjugate. If you think about some special cases we do when we multiply, this is kind of like our a minus b, this is kind of like our a plus b, which we know when we multiply out gives us a squared minus b squared. That is helpful in our problems that we did earlier. So let's go back to that problem. If I want to simplify this quantity here, 7 minus 3i divided by the quantity negative 2 plus 4i, what I want to do is multiply both the numerator and the denominator by the complex conjugate of the denominator. So I'm going to multiply this by negative 2 minus 4i. On both the top and the bottom. Now I do need to be careful. I want to make sure that I multiply it both on the top and the bottom, and it is a problem that you have to distribute. Now I purposely did this because we kind of already did our answer from earlier before. So let me see what we had for that. So we did this top part earlier. We did 7 minus 3i times the quantity negative 2 minus 4i. We did that back up here in number 3. And we got our answer was negative 2 plus 34i. So now what we need to do is the denominator. Now remember, for the denominator here, this is really like saying a plus b times a minus b. And we know that that's going to multiply into basically a squared minus b squared. So a is our value of negative 2. So negative 2 squared minus 4i squared. Negative 2 squared is going to be 4. 4i quantity squared is going to be 16i squared. But remember, I squared becomes negative 1. So this is really like saying 4 minus 16 times negative 1, or 4 plus 16, which is 20. So if I wanted to simplify this, I end up with negative 2 plus 34i over 20. And it's perfectly fine to leave this, but we probably should simplify. I do notice that I can divide all of these terms by 2. So when I divide everything by 2, I end up with negative 1 plus 17i over 10. Again, this is, it is a complex number, but usually in the back of the book they'll go ahead and separate the two of them. Unless I specify, it doesn't matter to me that you write it in either this form or this form. Just know that it should be a complex number. So if they say in complex form, technically that's in the a plus bi form. So that's going to be our answer for this one. So in order to simplify a problem where you've got division, remember that what you want to do is multiply by the conjugate of the denominator. So, on the complex plane, what exactly is a complex number? Well, when we talk about this idea of this a plus bi, what does it look like? We don't see these values because when we graph things on a Cartesian plane or a real coordinate plane where we only see real values. Well, the complex plane looks sort of like a regular coordinate system, with the exception of the fact that our axis, instead of x and y, is made up of the two parts of our complex number, a and b. So we graph our real value part of our number as kind of our x coordinate, and our b value kind of as our y coordinate. So if I asked you to plot the coordinate of the complex number, let's say 3 plus 2i, what it would be doing is basically plotting the point 3 for the real and then 2 for the non-real. So this would be the point 3 plus 2i. So for example, if I gave you a point right here, this would be the point negative 2 minus i. And of course, it doesn't have to have a value. Obviously, if I plotted a point here, this is basically the point, 1 plus 0i, or obviously just 1. And in the same respect, I could plot something along my non-real term here. This is like saying 0 plus 2i, or just simply 2i. So when they ask you to plot on the coordinate plane for the complex numbers, you're just graphing it kind of like the real and the non-real part for your x and y coordinate. So if you understand that, it makes this last thing very easy, and that is, what is the absolute value of a complex number? Well, if you think about what we just did in our last problem, when we look about a complex number, when we talk about the absolute value is always the distance from 0, or in this case, the distance from the origin. When we talk about the distance from the origin, we're looking at, say, for example, I have my origin right here. Let's say if I wanted to find the distance between this complex number and the origin, to calculate this, it would just basically be using the distance formula between these 2 points. Well, if we make this into a triangle, now we have a right triangle, and this is Pythagorean theorem. A would be our real part, B would be our non-real part, and to find the distance of this is kind of like our C of our right triangles. And using Pythagorean theorem, a squared plus b squared equals c squared. Well, I want to know the distance, which is c, so obviously it's going to be the square root of that quantity. And that's where they get this equation from. So the absolute value of a number is going to simply be the square root of the a squared value, the real part, plus the b squared value, the non-real part. We don't include I in there, we just look at the actual coefficients. So for example, if I wanted to find the absolute value of, let's say, for example, 3 plus 4i, I would take the square root of 3 squared plus 4 squared. I don't include the value of I. B is the value, the coefficient kind of in front of this value I. So this would just simply be 9 plus 16, or the square root of 25, which is 5. So that's how you'd find the absolute value of a complex number. Let's find the absolute value of this one. So I've got 2 minus 7i. We know we'd obviously take the square root of 2 squared plus, it's like saying negative 7 squared, because b is negative 7 here, so this would be 4 plus 49, the square root of that, square root of 53. And again, I can't really simplify that, so the square root of 53, you could just leave it like that because it's not a perfect square, and there aren't any perfect squares I can divide out of there.